from a planet ruled by creatures that make every living animal look small, to the world you were born into. 160 million years of dominance, of forests that no human eye has ever seen, of oceans that swallowed things whole and asked for more. Dozens of worlds rose and collapsed on this single planet. Most of them left no warning before they ended. This is the Earth before us. "66 million years ago, the sky split open. A rock 12 kilometers wide, traveling faster than a rifle bullet, hit what is now Mexico's Yucatan Peninsula and vaporized on contact. The energy released in that single second equaled billions of nuclear weapons. The temperature at ground zero reached tens of thousands of degrees. Every living thing within 1,000 kilometers was gone before it could react. And yet, before that moment, Earth had been running a completely different experiment for 160 million years. An experiment so vast, so alien, so unlike anything alive today, that if you had stood on this planet's surface during its peak, you would not have recognized a single coastline, a single forest, a single ocean current. This is not a story about one dinosaur or one species. This is a story about a world. A world that breathed differently, moved differently, burned differently. And we are going to walk through it together. From the scorching interiors of Pangaea's breakup, to the shallow inland seas that split continents apart, to forests where trees grew to heights that make modern redwoods look modest. If you are watching this for the first time, subscribe right now. We post documentaries like this every week, and I promise you will not want to miss what comes next in this one. The Mesozoic Era lasted roughly 186 million years. To put that in perspective, the entire span of human evolution, from our earliest ancestors to right now, covers maybe 6 or 7 million years. The dinosaurs had 30 times that. 30 times the span of everything that ever made us human, filled with creatures moving through continents that did not yet exist, breathing air that contained slightly different oxygen levels than today, under skies that tracked different star patterns. This was not prehistoric Earth in some vague, fuzzy sense. This was a specific, real operating planet that had rules, rhythms, and systems of jaw-dropping complexity. The story starts with the ground itself, because during the Mesozoic, the ground was moving. At the opening of the Triassic Period, roughly 252 million years ago, there was essentially one landmass: Pangaea, a single supercontinent so large it created climate conditions impossible anywhere on Earth today. The interior of Pangaea was a desert of almost incomprehensible scale. Rain fell on the coasts, then died before reaching the center. The monsoon patterns that fed the edges of this landmass were unlike any seasonal system operating on the planet right now. Temperature swings between summer and winter in the interior reached levels that would be lethal to most modern mammals. And this was the stage onto which the first dinosaurs walked. They were not giants yet. The earliest dinosaurs from the late Triassic were small, fast, bipedal animals. Eoraptor from what is now Argentina barely reached the hip of a modern person. Herrerasaurus was larger, but still nothing compared to what would come. These animals lived in a world dominated by other reptiles, by large crurotarsans, relatives of modern crocodiles, that had survived the end Permian extinction and still occupied most ecological niches. The dinosaurs were just one group among many, scrambling for their share of a tough, hot, seasonally brutal world. Then the Triassic-Jurassic extinction hit. Roughly 201 million years ago, massive volcanic eruptions ripped through what is now the Central Atlantic Magmatic Province, an area covering roughly 11 million square kilometers. Carbon dioxide flooded the atmosphere. Temperatures spiked. Oceans acidified. The dominant crurotarsans collapsed, and the dinosaurs, for reasons still debated, came through. What followed was one of the most dramatic ecological takeovers in Earth's history. By the early Jurassic, the dinosaurs had the world, but the world was changing fast beneath their feet. Pangaea was splitting. The rift that would eventually become the Atlantic Ocean was just beginning to open, a thin seam of volcanic activity pulling the supercontinent apart millimeter by millimeter. What had been a single landmass was fracturing into Laurasia in the north and Gondwana in the south, and between them, a shallow seaway was forming that would reshape every climate system on the planet. The forests of the early Jurassic were nothing like modern forests. There were no flowering plants yet, no grass, no fruit. The ground cover consisted of ferns, horsetails, and lycopsids. The canopy was conifer and cycad, plants that today survive only in relict populations in places like South Africa and the American Southeast. Walking through an early Jurassic forest would have felt like walking through something between a modern fern gully and a pine forest. But stranger, the smell different. The light filtering through leaves that had no modern equivalent. And through these forests moved the first of the genuinely large dinosaurs. Volcanodon, Barapasaurus, and early members of the sauropod lineage were beginning to push into size ranges the planet had never seen in a land animal. The sauropod body plan was, mechanically speaking, one of the most successful designs in vertebrate history. 4 column-like legs supporting a barrel-shaped body, counterbalanced by a long tail, the neck extending forward and upward to reach vegetation at heights no competitor could touch. The neck alone in later species like Brachiosaurus reached lengths of 9 meters. But here is what most people miss about sauropods. The neck was not just about height. Research into sauropod cervical vertebrae suggests many species held their necks more horizontally than vertically, sweeping wide arcs through low and mid-level vegetation, covering enormous feeding areas without moving the body. They were living harvesting machines, cropping cycad fronds and conifer needles from a sweeping radius, moving slowly, digesting constantly. Their digestive systems processed vegetation in quantities that would be impossible in any modern animal of equivalent size because birds and crocodilians, the dinosaurs' closest living relatives, both show evidence of highly efficient digestive strategies that extracted maximum nutrition from poor plant matter. Sauropods almost certainly used gastroliths, stones swallowed deliberately to grind vegetation in their guts, the way modern birds use grit. Whole deposits of these polished stones have been found associated with sauropod skeletons. The environments these giants moved through during the Middle and Late Jurassic were warmer and wetter than the early Triassic desert. Sea levels were higher. Shallow epicontinental seas covered parts of Europe, turning what is now a single continent into an archipelago of large islands. Temperatures at the poles were warm enough that there was no permanent ice. The planet was operating in what geologists call a greenhouse state, atmospheric carbon dioxide significantly higher than today, global mean temperature several degrees above our current baseline. This matters for understanding dinosaur distribution. There were no permanent climate barriers at the poles. Dinosaur fossils have been found in what was then polar latitudes, meaning some species lived through months of winter darkness and cool temperatures that would challenge the cold-blooded model many people still associate with these animals. The evidence from bone growth rings, from isotopic analysis of fossils, and from the sheer metabolic demands of large body sizes all points toward a more complex thermal physiology than simple ectothermy. Dinosaurs were not mammals. They were not fully cold-blooded reptiles either. They occupied a metabolic middle ground, and some lineages, particularly the small feathered theropods closest to modern birds, were functionally warm-blooded by any reasonable definition. If you are finding this fascinating and you have not subscribed yet, do it right now. Drop a comment telling us what country you are watching from. We love seeing where our audience is, and we read every single comment. The late Jurassic world, roughly 160 to 145 million years ago, was the peak of sauropod diversity and the ecological golden age of dinosaur dominance. The Morrison Formation in the American West preserves a snapshot of one ecosystem from this period with exceptional detail. Apatosaurus, Diplodocus, Brachiosaurus, and Camarasaurus were the dominant herbivores, multiple large sauropod species coexisting in what appears to have been a seasonal semi-arid environment with distinct wet and dry periods. How multiple giant sauropods coexisted in the same ecosystem without competing each other into extinction is a question paleontologists have been working on for decades. The best current answer involves niche partitioning at the level of feeding height and vegetation type. Diplodocus, with its horizontal neck and peg-like teeth adapted for raking, fed differently than Camarasaurus, with its more robust spatulate teeth built for tougher plant material. Brachiosaurus, with its upward-angled forelimbs and high-set neck, reached canopy levels the others could not. Same ecosystem, different restaurants. And then there were the hunters. Allosaurus is the apex predator of the Morrison Formation and one of the most well-documented large theropods in the fossil record. Hundreds of Allosaurus specimens have been recovered, from juveniles barely a meter long to adults approaching 12 meters. This depth of sample size tells us things that single skeletons never could. Allosaurus grew fast, reached sexual maturity relatively early, and suffered high mortality in its first years of life, a pattern more like a crocodilian than a mammal, suggesting prolific reproduction offset by brutal juvenile death rates. The skull of Allosaurus was not built for brute crushing force. The bite force was actually relatively modest compared to body size. Instead, the skull was light, fenestrated, built for speed and precision. The leading hypothesis for Allosaurus' attack strategy describes a hatchet-like strike, the upper jaw driving downward into prey with the neck muscles providing the power, rather than the jaw closing alone. This would have been devastating against the soft tissues of large sauropods, targeting flanks, necks, and tails, rather than attempting to bring down massive prey with a single bite. Evidence of Allosaurus-sauropod interaction shows up directly in the bone record. Diplodocus tail vertebrae have been found with Allosaurus tooth marks. Allosaurus bones have been found with injuries consistent with a defensive strike from a sauropod tail. These animals were not in a passive relationship. They were actively shaping each other's evolution, one predator and one prey population, locked in a biological arms race across millions of years. The oceans during the Jurassic were their own world entirely, populated by animals that had nothing to do with the dinosaur lineage. The Jurassic seas were dominated by ichthyosaurs, dolphin-shaped reptiles that had become so thoroughly aquatic they could no longer haul themselves onto land. Ophthalmosaurus had eyes roughly the size of dinner plates, adapted for hunting in low-light conditions, possibly deep water. Plesiosauroids were also widespread, the long-necked forms like Cryptoclydus using their four flippers to maneuver through shallow, warm European seas, hunting fish and cephalopods. Marine crocodilians, now extinct, occupied coastal zones. Metriorhynchus had lost the heavy osteoderms of its ancestors, streamlined its body, and developed a fish-like tail fin. It was a crocodilian that had essentially become a shark. These were not dinosaurs. These were parallel experiments in large body size and predatory efficiency running simultaneously in the ocean while the dinosaurs dominated the land. And above all of it, pterosaurs ruled the air. Pterosaurs are chronically underappreciated. Most people know them as the flying things in dinosaur documentaries, usually depicted as leather-winged backdrop creatures. The reality is that pterosaurs were extraordinary in their own right, with a diversity and ecological range that in some ways rivals the dinosaurs themselves. By the Jurassic, they ranged from sparrow-sized insect catchers to Rhamphorhynchus, a long-tailed form with a wingspan approaching 2 meters and needle-like teeth for snagging fish from the water's surface. Their flight membrane was not the simple sheet of skin it appears in old reconstructions. Fossil preservation from sites like the Solnhofen limestone in Germany shows that the wing membrane was reinforced with internal fibers called actinofibrils, giving it structural stiffness and the ability to change shape during flight with muscular control, far more sophisticated than a bat's wing in some respects. Pterosaur tracks preserved in mud show that on the ground they walked quadrupedally, folding their wings and moving on all four limbs, the wing finger tucked safely away from the ground surface. They were not clumsy on the ground. They were capable animals in multiple environments. As the Jurassic gave way to the Cretaceous, roughly 145 million years ago, the world shifted again. The breakup of Pangaea was well advanced. The Atlantic was now a real ocean, still narrower than today, but wide enough to begin separating the evolutionary histories of North America and Europe. Gondwana was fragmenting further in the south. India was an island continent drifting north. Australia and Antarctica were still connected, forming a landmass that sat at high southern latitudes, but remained largely ice-free due to the continued greenhouse climate. The single most transformative ecological event of the Cretaceous had nothing to do with dinosaurs directly. It was the rise of flowering plants. Angiosperms appear in the fossil record around 130 million years ago, and spread with explosive speed across the Cretaceous. By the end of the period, they dominated most terrestrial ecosystems. This transformation rippled through every food web on the planet. Insects co-evolved with flowers, developing new body shapes and behaviors to exploit the new resource. New groups of plant-eating dinosaurs evolved digestive strategies adapted to the tougher, more chemically defended tissues of flowering plants. Entire forest types were replaced. The Cretaceous world that most people picture when they think of dinosaurs, the world of Tyrannosaurus and Triceratops, was a flowering plant world, thick with vegetation types that would look more familiar to a modern botanist than anything from the Jurassic. The Cretaceous also saw the rise of some of the most morphologically extreme dinosaurs in the fossil record. The hadrosaurs, or duck-billed dinosaurs, developed cranial crests of bewildering variety. Parasaurolophus carried a backward-sweeping hollow tube of bone up to 1.5 meters long, connected to its nasal passages. The internal structure of this crest created resonating chambers. When air was forced through these chambers, the result was a deep, resonant sound that could carry enormous distances through dense forest. Hadrosaurs were herd animals. The evidence for this comes from bone beds, sites where dozens or hundreds of individuals of the same species died together and were buried simultaneously. Some bone beds contain animals of multiple age classes, juveniles alongside adults, suggesting family group structure similar to what we see in modern elephants. These were not simple, dim animals wandering through the Cretaceous. They were social, communicating, migrating herds of large-bodied herbivores managing landscapes at a scale that would have had measurable effects on vegetation structure across entire regions. The ceratopsians were equally extraordinary. Triceratops is the most famous, but the ceratopsian family tree includes dozens of species, each with a distinct combination of horns and frill. Protoceratops from Mongolia was sheep-sized and frigged, but unhorned. Styracosaurus had a frill ringed with long spikes. Pachyrhinosaurus carried a rough boss of bone instead of horns. The sheer diversity of ceratopsian headgear across closely related species strongly suggests these structures functioned at least partly in species recognition and mate selection, the way antlers and horns work in modern ungulates. The frill in many ceratopsians was richly vascularized based on surface texture analysis of fossil skulls, suggesting blood flow could change the frill's color and patterning, turning it into a dynamic visual signal. These were not simple beasts. They were animals with complex social lives playing out in the ecosystems of Western North America roughly 68 to 66 million years ago. And ruling over all of them was the most famous predator in Earth's history. Tyrannosaurus rex has been studied more intensively than almost any other extinct animal, and the picture that has emerged in the last 30 years is dramatically different from the one people carried through most of the 20th century. The upright, tail-dragging posture of old museum mounts is gone. Modern biomechanical analysis of the vertebral column and hind limb musculature shows T. rex held its body roughly horizontal, tail extended, counterbalancing the enormous head. That head was the weapon. At nearly 1.5 meters in length, it contained teeth the size of bananas, deeply rooted in massive jawbones. The bite force has been calculated at roughly 35,000 to 57,000 newtons, depending on the method used, substantially higher than any living animal, and enough to crush through bone completely. Unlike Allosaurus's precision slicing strategy, T. rex bit through bone routinely. Tyrannosaurus bones found with T. rex tooth marks show not just punctures, but scored and crushed surfaces where bone was actively chewed and swallowed. This was not finesse hunting. This was brute force resource extraction from the skeleton itself, accessing the fat-rich marrow that other predators could not reach. The question of how T. rex hunted, active predator, dedicated scavenger, or both, consumed paleontological debate for decades. The current consensus leans toward a flexible strategy, primarily predation with opportunistic scavenging, the way most large modern carnivores operate. The evidence for active predation is direct. Edmontosaurus and Triceratops bones have been found healed from T. rex bite marks, meaning the prey animal survived at least long enough for the wound to begin healing. A scavenger doesn't leave healed bite marks. T-Rex's sensory systems were exceptional by any measure. The olfactory bulbs, preserved in endocasts of the brain case, were proportionally enormous, suggesting a sense of smell comparable to modern vultures or better. The eyes faced partly forward, providing genuine binocular overlap and depth perception, useful for judging distance to moving prey. The hearing range, inferred from the legena in the inner ear, was tuned to low frequencies, the frequencies that carry furthest through dense vegetation. Every sensory system pointed toward an animal that was exquisitely well designed for finding and catching large prey in the forests and floodplains of late Cretaceous North America. The environment T-Rex inhabited looked nothing like the open savanna of most Hollywood depictions. The Hell Creek Formation, which preserves the last ecosystem these animals occupied before the end Cretaceous extinction, records a warm, wet, heavily forested floodplain environment. Mean annual temperature was several degrees warmer than modern Montana, where these rocks are now exposed. Extensive river systems cross the landscape. Seasonal flooding created oxbow lakes and swampy backchannels. The plant life included palms, ferns, dawn redwoods, and dense angiosperm understory. This was not open ground, where predator and prey could see each other from kilometers away. It was complex, broken terrain where large animals moved through corridors of vegetation, where ambush was as viable a strategy as pursuit, where the water table was close enough to the surface that parts of the landscape turned into shallow wetland during wet seasons. On the opposite side of the planet, separated by the Tethys Sea, a completely different set of dinosaur communities was running parallel experiments in large body size and ecological dominance. In what is now Africa and South America, the Titanosaur sauropods reached their maximum expression. Patagatitan majorum from Argentina is currently the largest dinosaur yet, discovered with a reasonably complete skeleton. Conservative estimates put its mass at around 70 metric tons. Its femur alone stood taller than most adult humans. Moving through the forests of Cretaceous Patagonia, Patagatitan would have literally shaken the ground, each footfall leaving craters in soft sediment. Its lungs almost certainly operating on a bird-like flow-through ventilation system based on the extensive air sac system evidenced by pneumatized vertebrae, would have processed air with extraordinary efficiency, sustaining a metabolic rate that could fuel a body of that scale. The predators that hunted or attempted to hunt titanosaurs were equally extreme. Giganotosaurus, also from Argentina, was a carcharodontosaurid theropod approaching 13 meters in length, potentially matching or exceeding T-Rex in raw size, though with a lighter, narrower skull and almost certainly a different hunting strategy. Maposaurus has been found in bone beds, suggesting possible group behavior. Multiple individuals of the same species dying and being buried together, which some researchers interpret as evidence of pack or social hunting directed at titanosaur prey. The evidence is disputed, but the ecological logic is compelling. How else do you bring down an animal the size of Patagatitan? In Asia, the Cretaceous was producing its own extraordinary fauna. The Gobi Desert preserves some of the most dramatic dinosaur fossils ever found, including the famous fighting dinosaur specimen, a velociraptor and protoceratops locked in combat, buried together in a collapsing sand dune while still grappling. The predator's sickle claw embedded in the prey's throat, the prey's jaws clamped onto the predator's arm. Two animals frozen in a moment of violence that happened 80 million years ago. Velociraptor in real life was nothing like the animal in popular culture. It was roughly the size of a turkey, fully feathered, with a killing claw on the second toe that functioned more as a gripping and pinning tool than a slashing weapon. Recent analysis of that claw's curvature matches the claw morphology of modern raptors that use their feet to restrain and control prey, rather than to cut. Velociraptor was a precision predator, probably hunting animals in its own size range, using speed, agility, and its grasping feet to subdue prey, and then delivering killing bites to vulnerable areas. The feathers were real. Quill knobs, the attachment points for wing feathers, have been found on Velociraptor forearm bones. It could not fly, the arms were too short, but it was a feathered animal in every meaningful sense. The link between non-avian dinosaurs and modern birds was not metaphorical. It was anatomical, developmental, and behavioral. The origin of birds is one of the most thoroughly documented evolutionary transitions in the fossil record, and it happened in the Jurassic. Archaeopteryx from the Solnhofen limestone of Germany preserved something extraordinary when it was first discovered in 1861. A skeleton almost identical to small theropod dinosaurs like Compsognathus, but with unmistakable feathers. Flight feathers arranged on the arms, contour feathers covering the body, a fan of tail feathers. Archaeopteryx had teeth, clawed fingers on its wings, and a long bony tail, features its theropod ancestors retained and modern birds lost. But it could fly, or at least glide in some fashion. Since Archaeopteryx, the picture of early bird evolution has become vastly more complex and interesting. Chinese fossil sites, particularly the early Cretaceous deposits of Liaoning Province, have yielded hundreds of specimens of early birds representing dozens of species, many preserving feathers in extraordinary detail, some even preserving melanosomes, the cellular structures that produce color, allowing researchers to reconstruct the actual color patterns of animals dead for 120 million years. Microraptor, a four-winged dromaeosaurid from these deposits, had flight feathers on both its arms and its legs, suggesting early experiments with aerial locomotion used multiple configurations that evolution eventually winnowed down to the two-winged design of modern birds. The polar regions of the Cretaceous deserve specific attention, because they challenge the simplest versions of the story. Antarctica, still connected to Australia, sat within the Antarctic Circle during parts of the Cretaceous, but remained forested with deciduous vegetation capable of surviving months of winter darkness. Dinosaur fossils have been found in these high-latitude deposits. Lea Elinosaura from early Cretaceous Victoria in Australia, which sat at roughly 75 to 80 degrees south at the time, had exceptionally large eye sockets relative to skull size, suggesting visual adaptations for low-light conditions, possibly allowing it to forage during the long polar winters when most modern reptiles would be torpid. This polar dinosaur evidence feeds directly into arguments about dinosaur thermoregulation. Cold-blooded animals at polar latitudes, subjected to months of darkness and cool temperatures, would need to either migrate or hibernate. The evidence from these high-latitude forms suggests at least some populations were resident year-round, which implies a level of thermal independence from ambient temperature that is fundamentally incompatible with strict ectothermy. These animals were generating at least some of their own body heat. The Cretaceous seas deserve their own chapter, because while dinosaurs ruled the land, the oceans had become dominated by one of the most formidable groups of marine predators ever to evolve. The mosasaurs, fully aquatic lizards related to modern monitor lizards and snakes, diversified explosively after the ichthyosaurs declined and disappeared near the end of the early Cretaceous. By the late Cretaceous, they occupied every ocean on the planet and had evolved body forms ranging from long, slender, eel-like hunters to massive, barrel-bodied apex predators. Mosasaurus hoffmanni reached lengths approaching 17 meters. Its skull, nearly 1.5 meters long, contained 2 rows of teeth, the main marginal teeth and a second set on the pterygoid bones of the palate, the same ratchet mechanism described in other large marine predators, designed to move prey deeper into the throat once seized. The jaws of Mosasaurus were loosely articulated at the midpoint of the lower jaw, allowing them to spread sideways to accommodate large prey, a feature shared with snakes that likely represents a shared ancestral adaptation. The Western Interior Seaway, an epicontinental sea that split North America from north to south during the late Cretaceous, was a prime mosasaur habitat. This shallow, warm, productive sea stretched from the Arctic to the Gulf of Mexico, essentially dividing the continent in two. On its floor lie the remains of plesiosaurs, mosasaurs, enormous bony fish like Xiphactinus, giant turtles, and countless other creatures that filled a marine ecosystem of extraordinary richness. Xiphactinus itself, at roughly 6 meters long with a gape large enough to swallow a human being whole, was the dominant fish predator of this sea. Specimens have been found with smaller fish still inside their stomachs, a last meal preserved for millions of years in fine-grained chalk. The chalk itself tells a story worth pausing on. The late Cretaceous saw a massive proliferation of single-celled algae called coccolithophores. When these microorganisms died, their tiny calcium carbonate plates settled to the seafloor and accumulated over millions of years into vast chalk deposits. The White Cliffs of Dover are Cretaceous chalk. The Niobrara Formation across Kansas and Colorado is Cretaceous chalk. These rocks were not deposited in deep ocean. They were deposited in the warm, shallow, productive seaway that covered the interior of continents during the greenhouse conditions of the late Cretaceous. Looking at the White Cliffs of Dover is looking directly at the seafloor of the Western Interior Seaway's European equivalent, the Chalk Sea, which covered much of what is now northern Europe during the same period. Above the late Cretaceous landscapes flew the largest animals ever to achieve powered flight. Asdarchid pterosaurs of the late Cretaceous reached wingspans that no other flying animal has matched before or since. Quetzalcoatlus northropi from the Hell Creek Formation of Texas had a wingspan estimated at 10 to 11 meters. Standing on the ground, it would have reached the height of a giraffe. How an animal of this size flew at all has been genuinely contested in scientific literature. Early analyses suggested Quetzalcoatlus was primarily a soarer, using thermal uplift to stay aloft with minimal energy expenditure. More recent biomechanical work suggests it was actually a capable flapper, launching by pole vaulting from all 4 limbs and achieving sustained powered flight. Ground-based feeding habits have been proposed based on its long, toothless beak and stork-like proportions, stalking across open floodplains and picking up small vertebrates and carrion, much like a modern marabou stork, but scaled up to something from a nightmare. These animals shared the sky with the first modern-type birds, which by the late Cretaceous had diversified considerably. Hesperornithiforms were large, flightless diving birds, fully adapted to aquatic life with reduced wings and powerful hind limbs for underwater propulsion. Ichthyornithiforms were more strongly flying forms with toothed beaks. The sky over the late Cretaceous Western Interior Seaway was layered with aerial predators of different sizes occupying different ecological roles, from small insect hunting birds in the shrub layer to Quetzalcoatlus patrolling river courses from altitude. The volcanoes of the Cretaceous Earth also demand attention because they were operating on a scale that has no modern parallel. The Deccan Traps, a massive flood basalt province in what is now India, began erupting roughly 66 million years ago, pouring lava across an area the size of modern France and releasing enormous quantities of sulfur dioxide, carbon dioxide, and other gases into the atmosphere over a span of hundreds of thousands of years. The Deccan Traps eruptions were almost certainly contributing to environmental stress on Cretaceous ecosystems in the final hundreds of thousands of years before the end Cretaceous impact. Some species were already declining. Some ecosystems were already shifting. When the Chicxulub impactor arrived 66 million years ago, it did not necessarily hit a perfectly healthy, stable world. It hit a world already under pressure. The impact itself generated a sequence of disasters that unfolded over different timescales. The immediate fireball and shockwave, the ejecta raining back down globally and superheating the upper atmosphere, the collapse of photosynthesis from soot and dust blocking sunlight, probably for years, the acid rain from atmospheric sulfur, the collapse of marine food webs as the base of the ocean's productivity shut down. The end did not arrive in a single day. It arrived in a cascade, each effect compounding the last over years and decades and centuries. The animals that survived were specific. Small body size helped because it reduced absolute food requirements during the period when food chains had collapsed. Generalist diets helped because specialists tied to specific food sources went extinct with those sources. Burrowing or aquatic habits helped because these environments buffered the temperature extremes of the immediate aftermath. Birds, the one lineage of dinosaurs to survive, were small, had beaks adapted for seed eating in many cases, seeds being one of the food resources that persisted through the impact winter, and many were likely capable of some degree of dormancy. The non-avian dinosaurs were none of those things. They were large, often highly specialized in their diets, and tied to intact food webs to survive. Tyrannosaurus needed functioning hadrosaur and ceratopsian populations. Hadrosaurs and ceratopsians needed functioning plant communities. Plant communities needed sunlight. When the sunlight went, the cascade ran its course in under 1 million years, geologically instant, biologically catastrophic. What remained after the dust settled was a world largely emptied of its dominant vertebrate groups, but full of survivors waiting for conditions to permit their expansion. The mammals that had spent the entire Mesozoic largely in the ecological margins, small, nocturnal, generalist insectivores, found themselves in a world with vacant ecological niches of every size and type. Within 10 million years, mammals had diversified into the full range of body plans and ecological roles we associate with them today. Whales had returned to the sea. Bats had taken to the air. Elephants and horses and rhinos were moving across the continents. But here is the thing people rarely sit with long enough. We are not the inheritors of a world that replaced the dinosaurs. We are the inheritors of a world that the dinosaurs built. The ecosystem engineering of large-bodied dinosaurs across 160 million years shaped soil chemistry, vegetation structure, continental geography, and ocean circulation in ways whose effects are still running in the world right now. The flowering plants that gave rise to our agriculture co-evolved with the browsers and grazers of the Cretaceous. The forest we depend on for oxygen and carbon storage evolved their basic architecture in a world being walked through by sauropods. The Mesozoic was not a rehearsal. It was a fully realized world, as complex and complete and surprising as our own, running on different rules for a span of time that makes all of human history look like a rounding error. We have only been recovering and reconstructing fragments of it from stone for about 2 centuries, and every year the picture becomes richer, stranger, and more humbling. Somewhere in rock that has not yet been found, in a cliff face that has not yet eroded, in a quarry that has not yet been opened, the bones of animals we have never imagined are sitting in darkness, waiting. The Mesozoic is not over. It just moved underground. If this documentary gave you something new to think about, leave us a comment below with the most surprising thing you learned. We genuinely read them, and they shape what we make next. And if you have not subscribed yet, this is your last reminder to do it. Every week, we go somewhere in deep time that most people never get to visit. We will see you in the next one.